Okay, yeah, welcome everybody back for this session. It's a great pleasure to be here. Thanks very much, Hussein, and also Vanderlei somewhere in the universe for inviting me here. For me, it's of course a little bit like coming back. I have very good memories of this place here. Fantastic to be here back. What I will talk about is some recent experiments that we had on non-equilibrium dynamics and some observations, discoveries that we made, which we are still trying to understand in more detail, but I'm going to share this with you in order to also stimulate some discussion. Just briefly, where is Heidelberg? Probably some of you guys know, but it's, as you can see, in the center of Europe, very close to France, has this old castle, very touristic place. What I also always like to mention, it's closer to Paris than to Berlin. That is somebody like me that was growing up in the Rhine, and that is very important. And we have this university founded in 1386. So it's the oldest German university. It's what we call a comprehensive university. So it covers all areas of research, humanities, medical centers, social sciences, and of course large departments for the sciences, mathematics, physics, and so forth. So in my group, we are studying several systems. One of the systems that we are studying is ultra-cold ion-atom interactions. We have an experiment where we are co-trapping negatively charged molecular ions. We can even cluster these ions so that with water, so that we can go studying chemistry in the transition from a gas phase, ion gas phase, to the liquid phase. We let them interact with rubidium, and there are some interesting things that you can observe once you have these systems cold enough and interact together. So that's one of the experiments. One of the things that I cannot cover today, but I amused myself a little bit with network science, trying to apply network science to many-body systems. There we are currently writing up a paper. Maybe we can discuss this in smaller circles. I already tried a little bit to discuss it here. So we said, let's take, for example, atomic spectra. Let's take the data of atomic spectra and map them on graphs, and then use graph theory from mathematics to identify, for example, something that you would call communities. And the surprise for me was that by even applying what is called agnostic approaches, we could find hierarchies in this graph, which then actually can be associated to quantum numbers. So without introducing quantum physics, we could see that there's structure in the system which is associated with quantum numbers. The surprise was, if you now go to very complicated systems like thorium, where there's lots of data available, you also find these hierarchies. Partially you can assign them to quantum numbers like parity and things that are conserved. Partially there is subgroups that are identified by these algorithms, by these mathematical algorithms to study graphs, that you cannot simply assign to quantum numbers. So maybe there is some group in Hilbert space. I discussed it already with Chris. Maybe there's something going on there that could help to then identify subspaces in a larger Hilbert space where there's some like of local symmetries or other things. I don't know. So that was that is a little bit of a toy game. It was just because I had some very gifted students here on the master level. Then there is experiments on Bose-Fermi mixtures. Maybe I'm going to just show two transparencies because Chris also showed it, and we had this graph. We had this other nice talk on Efimov physics, because that was the thing that we were studying there in the last couple of years. So we have this system where we have lithium and cesium. It's a system exactly of the kind that Chris was alluding to. So there's two heavy bosons and one fermion. And the interesting thing in this case is, first, you have an additional scale here in this problem, and that is the scattering length between the two bosons, so the intraspecies scattering length. Second thing that is interesting is that this is a good system to study, that can be studied to a first approach within a Born-Oppenheimer approximation. So you can understand lots of things on a, let's say, intuitive level. And the third thing, what is nice is that if you take this system with this large mass imbalance, this universality that you were talking about yesterday, the scaling goes down to a scaling that you can hope to observe several resonances. In this case, we always look at these three-body scattering resonances, that you can see several resonances and then directly see this universality within what is always called the window of universality, where the range that things should be universal is, on the one hand side, limited by short-range corrections, on the other hand side, by the temperature that you can achieve in the system. And you can see, for example, here in this graph, this is the scaling factor that we were talking about, that this is 22.7 if you have homonuclear systems. This is the scaling factor now under different scenarios. This is if, in both cases, that the scattering length between the bosons and the fermions is infinite, but this is now the two cases where, for example, one is this interspecies scattering length is 0, and here is infinite. And you can see that, of course, the scenario or the scaling factor very much depends on that. And you can also see here the line of the Born-Oppenheim approximation, and you can see that where lithium-cesium sits, that is here, they seem to fall more or less onto each other. And then we were lucky. We were lucky because, as it turns out, we have a nice set of Feshbach resonances in this lithium-cesium system. And that was what also Chris already mentioned. There is one Feshbach resonance for lithium-cesium where the cesium-cesium scattering length is negative. So that is the scenario that is typically being studied. But there was also one where the scattering length of the cesium-cesium atoms is positive. So that is the scenario where you have a bound cesium dimer, actually. And that is the scenario in which we also don't observe the lowest Efimov state. So the Efimov states we observe by directly measuring the three-body loss rate, the loss coefficient. We map this out, and then one sees these characteristic resonances. And you can then see the scaling. This is calculations where you can also see how these states then asymptotically go to these bound Efimov states based on the calculations of Chris and co-workers. And you can see also nicely that in the case of the positive scattering length, this lowest Efimov state is actually not converging to a three-body resonance, but is converging to the cesium-2 plus lithium threshold. That's why we don't observe this Efimov resonance in the loss spectra that we see. You can also see that there's very good agreement with this van der Waals model of Chris and co-workers for negative scattering length. Qualitatively, I would say there's also good agreement for this positive scattering length, but you can see that there's still some details that are fitting better or worse, matter of taste. So there's still things to be discovered in this kind of system. But grosso modo, I mean, we wrote some papers here in the last couple of years. Here, this last paper, 2017, somehow gives a summary, if you like, the latest, at least our latest best insights of this entire system. There's a review that we wrote here 3 years ago, and there's other papers where you can find details. So that is the lithium-cesium system. We are currently moving towards polaron physics because there's interesting proposals that within the lithium-cesium system there is an interesting interplay between this few-body Efimov physics and the polaron scenario, so that there's some kind of hybridization of the polarons with trimers and vice versa, so that there should be some effects where the Efimov scenario comes back into the many-body polaron scenario. So that's what we are currently after, and that is what the experiments that we are currently doing this. But what I would like to talk about today is our experiments on Rydberg atoms. This is a field that exploded in the last, I would say, 5 to 10 years, more and more groups. In Germany, we have a priorities program by the German funding agency, and I think it's 20 plus groups actually in this priority program alone. And in the US, there's big programs, lots of groups in many places worldwide these days. I do this in Heidelberg, but I also started an activity at the University of Science and Technology of China, which is based in Hefei, but I'm having these experiments in the Shanghai campus, where we are using strontium-2 electron systems to study or to use Rydberg atoms for quantum information. But what I'm talking about today here is the results that we have from my Heidelberg group. So let me start to give an introduction why we are interested in these things, and I can directly build upon other talks that we had before, José Dincao asking the question, how do actually systems reach equilibrium, isolated systems reach equilibrium? In Heidelberg, we have an entire priority program or a priority center that is just asking this question, exactly this question. It's called ISOQuant, Isolated Systems Quantum Dynamics. And one of the major examples is, for example, a system of spins. I mean, this we all know. We have these magnetic spin interactions, and although we know magnetism since centuries as an effect, we still have a hard time to understand it based on microscopic principles. Although the Hamiltonian that governs these interactions is very simple. I mean, it's these Heisenberg-type Hamiltonians. You have two spins that interact via some coupling constants Ji, J, And then it depends, of course, on the topology and on the structure, how these JIJs look like. They might be ordered, like in this example. They might be disordered. There might be long-range interactions, dipolar interactions. There might be just contact interactions. But anyways, that is a harmless, simple-looking Hamiltonian, but we all know that it's impossible to predict many of the features of magnetism from these first principles these days. And of course, the important thing here that governs this entire system that has to be understood is how correlations emerge. Correlations, be it classical correlations or quantum correlations in terms of entanglement. So it's usually, or in many cases, it's simple to find the ground state of such systems. For example, if I take this Hamiltonian, if J is positive, I get a ferromagnet. If J is negative, I get an antiferromagnetic ordering. This is the simple cases. But already if you have, for example, now a situation where these, in a ferromagnetic case, there you have this broken symmetry here, and then the question is, what happens in between? There's the question on how these domain walls are actually being formed and how they change with time and stuff like that. So there's lots of interesting questions, and they become even more interesting if you also include now external fields, and you see the transition then from paramagnetism to ferromagnetism by just adding this additional magnetic field with a certain coupling strength, omega, here on the single spin level. So, and this, actually, I wrote this before José's talk, but it's exactly posing the same questions. So what is the phase structure of such systems? So can we understand in the 1D, 2D, 3D, can we understand the different phases that we have? How do the correlations actually influence the dynamics of the system? And that was the question that you also posed. How does such a system, be it ordered or disordered, how does it actually reach equilibrium, and what governs this dynamics? So for this, we need quantum simulators, so I refrained from putting Feynman's famous citation here. I took a rather recent one by Case and Hazard, and I hope that there's no theorists in the room, because what he says is, to describe what a quantum simulator is, I will first have to disclose a fact that is particularly painful for us theoretical physicists. We can rarely predict the behavior of quantum systems where more than a few particles are interacting. This is not a consequence of limited mathematical prowess or computing power, but the fundamental difficulty of solving quantum mechanics with classical machines. So the aim of a quantum simulator is now to solve this problem, and that's interesting that a theorist says this, yeah. If you want to know the underlying properties of a certain quantum system, then build another controllable quantum system. So I invite everybody of you guys to come to the lab and to help us doing that the next time. And then it's the old idea, of course. You want to have a system that describes the underlying Hamiltonians, and then you can let this system evolve, and you can see what this system gives. So Rydberg atoms is maybe not the first thing that you might come about when you talk about quantum simulators. There have been all these other systems, but maybe let me introduce this Rydberg system a little bit more in detail. As you can see from this graph, we talk about highly excited states, Rydberg states of particles, and then you can see that if you just go high enough in principal quantum number, every element looks like hydrogen. And that is because you have this shielding of the inner electrons by the core, and then if the electron is not penetrating this core, you actually get Rydberg's famous formula, and if it penetrates it, you also get Rydberg's formula, but now with what we call in modern language this quantum defect that tells you how much you still have to correct the Coulomb potential in order to get the effects of the finite influence of the inner core. And as you can also see, as the higher the angular momentum, the smaller is the influence of this core, because if you have high angular momentum, this electron doesn't even penetrate the core. That you also see here in this, comparing this. For high L, this really looks like hydrogen. So this is great as an experimentalist, because you can choose whatever element you want a priori, just excite it high enough, and then it will look like hydrogen. Don't need to worry about that. And the calculations of this quantum defect are so simple that even I understand them. So what is interesting for these Rydberg atoms is they were used in the 80s to be good examples for this transition from classical systems to quantum systems. And one of these examples is if you look at the classical probability of finding, for example, the sun around, the Earth around the sun, or an electron around the proton, then it's this characteristic charge density distribution that you have. And if you compare that now with the wave function, for example, of a state that has n equals principal quantum number of 100, then this is pretty close to this classical distribution function. So that was one of the things why people studied the transition from classical to quantum for many, many years using Rydberg atoms. And also Fermi's contact was introduced by studying spectra with Rydberg atoms, as Rydberg atoms were being also used by Rydberg to create his famous formula. So these atoms have these highly excited atoms have quite a history in modern AMO physics. So this is just to give you an idea of the scales. So this is here the wave function of a Rydberg atom with n equals 30, and this is compared here to the ground state of hydrogen. This is this dot here that you cannot see. This would be DNA. This I took from Serge Roche's lecture, so ADN in French. It's much larger than that. This is the size of a tobacco virus. So it's as big as a virus. And the world record these days, here in this paper, 2012, is n equals 600, so the orbital radius is as big as a hair. So this electron is really, really far away. And that means it's far away from the core. That means the field of the core is small, and then any kind of outer perturbation will have a big effect on the electron. And that means that these electrons have interesting scaling properties. So we know that the binding energy goes like 1 over the principal quantum number squared. The radius like the square of the principal quantum number, so typically 500 nanometers if you go up to n equals 100, typically. But what is most important in our context is this huge polarizability. It scales like n to the 7th, and that has to do with this small effect of the remaining core field on the electron, so any kind of outer field will have a large impact on the electron motion, creating large dipoles in an electric field. So what is the effect of this in terms of interactions? You can have several kinds of interactions in these Rydberg atoms. For example, if you take two states here with L equals 0 here and L equals 1, so different parity, then they will interact via the 1 over r to the 3 resonant dipole-dipole interaction in this case. And typical scales of this dipole moment are of, in chemical units, thousands of dBi. So typical dipoles like water have a few dBi. So this is 3 orders of magnitude larger dipole moments that you have here. If you take states of the same parity, then it depends on where you are with respect to an intermediate state of different parity. And that is because of the structure of this dipole-dipole interaction Hamiltonian. So this distance is given here by a Fursa defect, just the detuning of these two levels here from the intermediate level. And if you take this now as a quantity, this defect, then it depends. If your detuning is small, you find dipolar interactions because you have dipolar interaction now via this resonant intermediate state. This is called Fursa resonances. But if you're far away from that, if this detuning is large, then you will retrieve the well-known van der Waals interaction. So that means if you tune this intermediate state, and this you can easily do by electric fields, you can not only tune the strength of the interaction, but you can also tune their nature by going from a 1 over R3 to a 1 over R6 interaction. That depends on the structure, yeah. It's a little bit depending then on the principal quantum numbers and so forth. In our case, rubidium, the S states, L equals 0 states, they are generally repulsive. But you might have attractive interactions. I am going to show to you in a few minutes a system where we have both interactions at the same time. So you have to now envisage, this is the atoms. The electron has a certain size, let's say a few hundreds of nanometers. That is the typical dimensions. And now we have another atom that is at a distance of several micrometers. So if they were in the ground state, there would be no interactions at all, or very small interactions, totally negligible. If they were spins, like also what we had on this workshop, magnetic spins, there would be a finite interaction. This is shown here. If the distance is a few micrometers, this is the interaction in hertz. This is always spanning here 4 orders of magnitude. This would be van der Waals interactions. You can totally ignore 10 to the minus 9 hertz in frequency units. Magnetic dipole interactions, they could be significant, already of the order of couples of hertz. And if you take Bose-Einstein condensates or Fermi gases, that is a significant order of magnitude already. But if you now go to Rydberg states, you crank these interactions up by 12 orders of magnitude. They become huge. They become megahertz. So that means you can do everything fast. Everything happens on very fast timescales. That is important because at this moment you can also consider this gas to be a frozen gas. So you have this cold atom gas, you excite it to Rydberg states, everything happens in a few microseconds. At this during this time you can consider, to a good approximation, the atoms to be frozen. Yeah, you have higher order corrections to the interactions indeed, yes, depending on what their distances is. There's another interesting effect that is also depending on the distance. You get a crossover from a 1 over R6 to 1 over R3 interaction because of other levels coming in, pair states coming in, and also that is another way to tune the interaction is not only by the principal quantum number, where there's this n to the 11 scaling, but also by the distance you can tune the interaction. Okay, so that means it seems to be a great system to do some kind of quantum simulation because you have lots of degrees of freedom under control. In particular, the interactions you can tune over a vast range. So I would say that was a very decisive paper because that stimulated lots of us people to think about using Rydberg atoms. There's a question?
Just what is the typical lifetime?
The lifetime of n equals 100 states is typically a millisecond or so. Hundreds of microseconds, milliseconds. But we never use these long time scales because even on shorter time scales there is forces. For example, we had a paper 10 years ago where we showed that by these forces there's also motion of the atoms and they get close to each other. At this moment they undergo penning ionization. So a pair of Rydberg atoms undergoes penning ionization if they get very close. So you want to avoid that. So typically, although the lifetimes of these states can be of order milliseconds or larger, you try to have experiments on 10 microsecond scales or shorter. So everything I'm going to show today is going to be happening on a microsecond time scale or even shorter. Very fast, and the great thing about it is if you compare this, for example, with experiments with molecules, dipolar molecules, where you can see similar features, you can map this one-to-one. Here we don't need to worry about single particle decoherence effects because typically noise in your lab is strongly reduced, magnetic noise, electric noise, at frequencies of megahertz or faster or higher. So what I wanted to say here is lots of things started with this really visionary paper. It's a little bit of who is who in modern AMO theoretical physics. I don't know who actually wrote this paper, but the great idea was, I mean, if I take now 2 ground state atoms and I excite one of them into a Rydberg state, that's fine. But due to these interactions, I get a repulsive, in this case repulsive interaction, and the distance is short enough, then I can no longer excite the second Rydberg atom. So I get a blockade effect. So within a certain critical radius, which is given by the width of this resonant with respect to the interaction, I will have a certain radius to within you. I have only one Rydberg excitation at a time, deterministically. So I create a mesoscopic ensemble, but I can know for sure that there is no pairs within this radius, critical radius, which we call the blockade radius. And the interesting thing is that creates also an interesting many-body state because since this is a delocalized excitation, I have to write down the wave function of this single excitation like this. So it's an exciton. You can consider this an exciton. And I can still describe everything now more or less by a 2-level system again, but with this delocalized excitation. So everything scales by this cooperativity here, and therefore you get a square root of n in the Rabi frequency and other things where the number of atoms enters. So this is what we call the so-called super atom picture these days. So that is an interesting effect, and that sparked an entire, I would say now, industry, more or less. More and more people entering. I don't even try to make a list of which people are working on Rydberg atoms these days. But what you can see is that there's different fields that are covered. Chris already alluded to this part. Few body physics, Rydberg molecules, very interesting stuff going on there. That was what Chris was talking about. Quantum optics is an important thing. You can use this now to create deterministically single photon sources by using EIT conditions. Quantum information processing, that was the original intention also by this blockade paper of all these guys. This turned out to be very difficult, but it's still also a subfield in what we are doing. Energy transport, you can mimic energy transport in these systems very nicely, as we could show some years ago here in this paper. Structure formation, crystal formation, you have a self-emergent scale that is this blockade radius, so you see interesting self-emergent structures. But what I want to talk about most today is this kind of quantum simulation aspect, so mapping it now on some kind of interesting classes of Hamiltonians. Yes?
Yes, you may choose to answer this later or not at all.
Yeah, it's because so far the gate fidelities that you could create with these systems were of, I would say, at current level limited fidelity. If you compare it, for example, to ions, where you have incredible fidelities. So you're competing. If you think about digital quantum computing in this case, you're competing with the ions, where they have these fantastic fidelities already. But I would not exclude that. I mean, we have seen, this field has gone through many stages. There's many things that we do now that I would have never considered possible 5 years ago in terms of control. So there's, of course, groups around that have new ideas, like Mark Sefman, using now a whole manifold of states, not only 2 states, to encode quantum information. And then you might enter into more robust gate topologies, and suddenly you might be again compatible, or let's say competitive with the other quantum information guys. And for neutral atoms, I would say still this Rydberg interaction is probably the best interaction that you can use to entangle 2 atoms. I think it is a little bit also fashion. Where is the field going and who's doing what? So I wouldn't exclude that, but there were some papers here like almost 10 years ago that showed that you can make gates and that you can use it in the classical quantum information sense. Since then, there hadn't been too many papers, at least on the experimental side. Yeah, but I'm sure that there will be soon more things to come. But at the moment, I would say this quantum optics is super active. Yeah, here quantum simulation, energy transport, these kind of things, because that is also very exciting because it gets us into connection with fields that we were not connected to originally. All right, so why this is interesting for quantum simulation? I told you already that we have this tuning of the interactions that we can use. And now if you look at it, there's several ways how to create now spin Hamiltonians. One possibility is you'd use the ground state as one pseudo-spin component and the excited state as the other one, spin down, spin up. This you couple by for example, by a laser field. And what you get then is this van der Waals interaction that gives you then a quantum Ising model, because you have effectively a interaction between atoms in this excited state. Just to give you one example, this is a beautiful paper here by Antoine Broweys in Palaiseau Institut d'Optique, where they can now create single atoms at more or less at will in a 2-dimensional geometry. And what they did is they illuminated them here, and this realized an interesting Ising model, and then they could map out, for example, the correlation functions. I think theory was done by Tommaso Macri here in Brazil. So they see interesting already simulations of Ising models, and there's other examples by many groups. Yeah, Michal Lukin, Markus Greiner, Vladan Vulicic, Emanuel Bloch. We did some experiments with in Okazaki with Kenji Omori. So this is one possibility to implement certain kinds of classes of Hamiltonians. What we got more interested in recently is now to use, instead of the ground state and a Rydberg state, use 2 Rydberg states as the 2 components of your pseudospin. So you can couple them by a microwave. That gives you this additional magnetic field that is required. The detuning will play the role of a Z component here. And if you have this configuration with 2 different parities here, you get a dipolar XY Hamiltonian. So Heisenberg XY Hamiltonian. If you go one step further and you use a 2-photon coupling, and that is easy to be made in Rydberg atoms because they have these huge dipole moments, they also couple very strongly to microwave fields, you get a Heisenberg XXZ Hamiltonian. And that is the one that we were currently using. So what I'm going to talk to you now is using this kind of configuration and studying now the Heisenberg XXZ Hamiltonian. So what we have in our case is a disordered system, to a certain degree disordered. I will allude to this in a few minutes again. But you can consider this now a gas of frozen particles, frozen spins, with a certain kind of disorder. And we know that in these disordered systems, there's an interesting competition between ferromagnetic and antiferromagnetic interactions. Frustration is an important word in this context. And it is you can directly compare this now to spin glasses that were studied for many decades these days. This is just one example of a spin glass. So here's the magnetization of a spin glass, and one of the things that people got interested was that these glasses have this very slow dynamics in the magnetization. You can see that this magnetization now here is very slowly decreasing. So that's why I was asking, is there an equilibrium state or not, or what does it mean? This is typically systems that are in thermal equilibrium with some kind of surrounding. But the question is it really thermal equilibrium that you have, or what governs the dynamics? And you can see that this is governed by scales that are covering many orders of magnitude. This decay is almost logarithmic, yeah? This decay of the magnetization. So how do we do this? So this is a sketch of this is a photo of the experiment. So we have a classical BEC experiment. There's some Rydberg stuff inside, so we can control electric fields. We can field ionize the Rydberg atoms and then count the ions, ion by ion, so we can nicely make counting statistics. That's all things that we did in the last couple of years. We can create a BEC within 3 seconds, but we don't use this BEC because the densities are much too high for what we want to study. I showed to you that the typical distances are micrometers, so we want to have densities of the order of 10 to the 12 atoms per cubic centimeter. Not more than that. So what do we typically have? 10 to the 4 rubidium atoms in an optical dipole trap at a decent temperature. So then what we do is we excite these atoms into one of these states. And that a priori creates a pure spin state. So in principle, we have no entropy in the state because we excite only exactly one state. Yeah? This excitation is already governed by the dipole blockade, so that means we have some scale here in this problem. We will never excite 2 atoms that are closer than this characteristic blockade distance. That is important for the following. So it's not a totally random sample, but it's a sample that has a certain cutoff in terms of interparticle distance. So then what we can do is we can, for example, drive this system by a microwave, and we can study what the system does in this microwave field, in this transverse field, and we can look at the dynamics of the system under the action of this pseudomagnetic field and the action of this interaction. And in our case, for what I'm going to show now, we are using this the XY interaction for the first experiment I'm going to show here. So what did we observe first? And this is published last year. So what we observe is Rabi oscillations, as you would expect. So you drive this spin system and you observe Rabi oscillation. Here in the language of magnetization, this is an oscillating magnetization, but this is just the fact that you now, in the Z direction, yeah, you just go between the ground state and the excited state.
Did you say that, or your previous graphs say that all the spins were initialized parallel?
Yeah, in the Z direction. I mean, this is what you do, is you start with this pure state. So that means you have a polarization in the Z direction.
Parallel in the plane of a pancake? This is a pancake?
It's a 3D configuration. It's a 3D gas. It's a 3D gas, and it's Z in the frame of defined by these 2 spin states. So there's no spatial frame associated with that in the sense, yeah. Because it's these 2 states here.
There's a trap and it has some geometry.
Oh, that's a 3D geometry. It's a
Cigar-shaped?
cigar-shaped trap, but we don't have a particularly small dimension in one of the directions. So we assume this to be a 3-dimensional system. Yeah? We are currently playing with geometries where you go below the blockade radius in 1 dimension or 2. That's a different story. But here everything is large compared to these scales. Yeah, all rotating. Which in this case is fine. But we can include the other term. I mean this one. Yeah. Yeah, so the typical distance is of order micron. The wavelength is larger.
So these Rabi oscillations are single atoms?
Let's talk about it right now. So in principle, it's single atom effects. Yeah? In principle, it's single atom effect, but you see, when we change the density, they damp out. There is no single particle decoherence, at least not on the level that we can see here, on the level of precision that we have. So I first thought, okay, that's easy to understand. What we have is a typical mean field effect. So you have all these other spins around. They interact via this, in this case, this XY interaction. So they create a local field, different local field. For each atom, this is slightly different. And therefore, we see this as a kind of dephasing.
So it's like T2?
Yeah, in this language. Mm-hmm. But it turns out that that was too narrow-minded, too naive. Because what we did is then we did a careful analysis. So the first question we had to answer is this an isolated system? Is it really an isolated system? So what we did is we chose one of the methods divided here by Caden Hazard and others, Anna Maria Ray, where you say, okay, I do a simulation that is based on certain clusters of finite size, 10, 12 spins that I can still solve, and then I just average over these clusters. And I use the Hamiltonian that I think that I have, and that gives me then a certain average magnetization. And as you can see, this is nicely fitting our data. It's not even fitting. Reproduces our data. Let's put it this way. Yeah. This reproduces our data if you plug in the densities and what we have. So the only free parameter that we have is a volume. And then you can fit all curves with this one free parameter. Okay, so then we thought, okay, let's use another method, mean field. That was my original naive expectation. And use a classical statistical method that goes under the name of discrete truncated Wigner approximation. So what you do there is you start with the pure quantum system, so the pure quantum spins. You map this density matrix on a Wigner distribution. So that gives you some kind of quasi-probabilities. And then you let this system, you take this as a random configuration, and you let this system evolve classically. So that helps you now to solve the many-body problem, because you only have to solve now a classical equation of motion, but what you plug into is what I like to call the primordial quantum fluctuations. So these are in the model through this Wigner distribution. This is a paper where this method, also Anna Maria Ray, Johannes Schachenmeier, where this is explained. And that turned out to be, is also a good method for certain systems to be studied, to study the evolution. And the interesting thing is that, and this is this graph here, that both this full quantum method, with this averaging of course, and this classical statistical method seems to reproduce our data pretty well. So what you see here is for different interaction strengths. So this is all these graphs here, but instead of now plotting all these curves, we plotted the Fourier amplitudes. And this is reproducing this very, very well, whereas the mean field quantitatively fails. Qualitatively, I would still say it's okay, but quantitatively it fails. In terms of the absolute amplitudes here, it gets better and better the larger the interaction, this mean field approximation. Okay, so the green curve is the mean field. This classical statistical, this truncated Wigner is the red one, and the black one was the original one that I showed, this moving average cluster expansion. So, as it seems already here, you see clearly that this system cannot be described by a mean field theory, yeah. At least quantitatively. Qualitatively, I would still say yes. All right, and what it was interesting too in this part of the experiment, and I think this is probably, it's not clear at all why this is sufficient. It is sufficient if you just measure the magnetization. It's sufficient to have this classical statistical theory, which means it's sufficient to only include the initial quantum fluctuations, which then lead into correlations with the dynamical evolution, but you don't need to trace the full quantum mechanical evolution in order to capture the essence of the magnetization here. So that is still a surprise to me, but it has to do with these methods or how this system evolves. I can't give you a deeper explanation for that. But that's how it is. All right, so primordial quantum fluctuations determine the subsequent relaxation, or dephasing, maybe I should say. Okay, then we said, okay, what kind of experiment could we possibly do that we do not simply have a quantitative, but really a qualitative breakdown of the mean field approximation. And so the simplest experiment that you can do then is you can excite your spin state, and then instead of studying the evolution of the Z component of the magnetization, you excite the system, or you not excite, you transfer the system into a spin that points into the X direction. So this you do by a pi over 2 pulse. So we shine in a pi over 2 pulse, and this pi over 2 pulse creates a spin that points in the X direction. And now we can look at the evolution of this spin in the x direction under the action of this Heisenberg Hamiltonian. And now this was your question. What is the interactions that enter here? So it turns out that here the dipole-dipole interaction has a different sign than the van der Waals interaction for this specific situation. They are almost equal in magnitude for this specific end state that we use. I think it's a factor of 1.6 or so, if I remember correctly, but they have opposite sign. But you might choose other states, and then this would look different. So you look at the evolution, and then you do what everybody does. You do a kind of tomography of your spin again with your microwave. And you check what is the final spin. So now, in this case, mean field evolution is very simple. Nothing happens. Because what you take now, this mx state, is an eigenstate of the eigenstate of the mean field Hamiltonian. Yeah? Because here, this is then you have a finite value here. This is 0, so this is an eigenstate. Okay, I could show you this if I could manage to get it. Oh, it runs. Okay. So this you see in the simulation as well. If you just do the simulation, this is now a full quantum calculation with how many particles we can choose. Yeah, you see that really in this mean field approximation, everything gets stuck. So it's self-locking because all the spins point in the same direction, so they lock themselves. But what you observe is a relaxation of the magnetization. Yeah. And you see that this is simply a relaxation of this x component, of the x component. The z component stays 0. And now, this of course deviates, as I said, from what you would expect from mean field. Now it's no longer some quantitative argument here, but now it's clear that mean field is totally off. Now we did this truncated Wigner approximation, this quasi-classical approximation. That again seems to match the data quite well, in particular for long times, which is again surprising why it should match so well for long times, because it's not actually made for studying long times. It doesn't fit so well, you can see here in this short time part. So, but taking now these quantum calculations, what you can see is that this evident decay of the magnetization is actually due to the buildup of correlations and entanglement. Because you have the interactions and they build up correlations, and these correlations lead to a decrease, to a relaxation of your total magnetization. So that is what you see here in these calculations. This is some real quantum calculations here for 8 particles or 10 particles. All right, so what can we do next? So what we did next is we chose now a purely heuristic function from a typical spin glass physics. So typically what the people observe there is that these relaxations can be very well described by a function that is a stretched exponential function. So you have a function which is an exponential, but here there's an additional exponent beta. And this beta tells you, if beta is 1, of course, you have a pure exponential decay. If beta is 0, you have a pure logarithmic decay to lowest order. So this gives you a quantitative means to tell where am I with respect to logarithmic or exponential relaxation. And as it turns out, this beta is somewhere in between in our case, 0.4. Yeah? And this is typical, what is typical called glassy dynamics. Not really aging, I should say. It's glassy, it's called glassy dynamics. People find the same thing. So now we can go next step. We can say, okay, how does that scale now? Is there some kind of simple scaling in this? The simplest scaling that you can have is, of course, that all these coefficients here, these coefficients, coupling coefficients, they scale as 1 over R6. So if I transform this into a new time by just rescaling time via this C6 over A6 scaling, then I can try to see what happens. And what happens is, this is now the data that I showed originally, these green dots. And this is now a whole set of different measurements at different densities. And you can see that they all seem to fall on some kind of universal line, which is surprising because we have this blockade. This blockade, if I change the density, the effect of this blockade on the distribution of the coupling strengths is of course different if I go to different densities. Yeah. So long distance, they all look the same, but it's, of course, if you go to higher and higher density, this cutoff makes a higher effect on the coupling strength than if you go to lower densities. So in order to capture this in a quantitative way, what we did is we introduced the Kullback-Leibler divergence to quantify this distribution function, or the degree of disorder. So the Kullback-Leibler divergence is nothing but the entropy of the pair correlation function. So consider this a means to quantify disorder. So if you have a full disorder, this Kullback-Leibler is 0. If you have a lattice, it's infinity. Yeah? And as it turns out, and this is now the fits for these different values for the different measurements that we have have a certain range of Kullback-Leibler divergences, but this beta coefficient seems to be always the same. That's why all of them fall into the same curve. And this is surprising. It means that if disorder is large enough, it doesn't depend on the disorder anymore what the characteristic dynamics of this magnetization is. Yeah. So in order to investigate this a little bit further, we now took this theory, this quasi-classical truncated Wigner approximation, and we studied this now over a wider range of densities than we can do in the experiment. And indeed, also for this quasi-classical calculations, you can see that if the density is small enough and the degree of disorder is is large enough, then all these magnetization curves here, if you wait long enough, they seem to fall on a kind of characteristic universal relaxation curve. They deviate, of course, at shorter times, because at shorter times you have quadratic behavior. I mean, if you have a perturbation theory, everything will start quadratic, this Hamiltonian. So this is clear that in the beginning you have quadratic dependence. If you have high density, which means you get ordering almost not a lattice, but you get high degree of correlations to this blockade, then you see additional structure on this magnetization decay, and it no longer falls onto this universal curve. And if you capture this now in this beta parameter versus the Kullback-Leibler, you can see that up to about 1 in Kullback-Leibler divergence, which I don't know whether it's a coincidence or there's some meaning behind it. If you're below 1, everything seems to be universal in terms of this magnetization relaxation. If you go too high, if the order becomes too large, then it deviates. Yeah. Okay, that's what we find. All right. So what we are going to do next, we did it already actually, we can now also apply a magnetic field by just driving the system, which breaks the symmetry. And then we can check what this magnetization is going to do. That's another point where we see that we have an isolated system, because if we start with a magnetization like this and then we change the magnetization abruptly, for example, to the opposite side, the spin will still stay locked in the original direction. This is what you see here. So this is the magnetization as a function of the external field. Here you see the characteristic magnetization curve, which you would expect, and for an equilibrium system, you would expect that to go below, to go negative when you switch the magnetic field in the opposite direction. But in our case, it just goes back to the original state, which shows that it's isolated to a certain extent, because otherwise it would find its way to the ground state. And it turns out that we can neither reproduce this by any kind of the theory, so we are having trouble here. And the other thing that we want to do is now study susceptibilities, because that gives us direct access to properties like aging in spin glasses. That is called aging, the dynamics of the susceptibilities. We want to study the fluctuation dissipation theorem in this system. And what we would also like to do, and this is something that we can easily implement in our system, is study how does a domain wall actually, what happens at a domain wall. So we just excite one spin state in the one half, another spin state in the other half, and then we look how this domain is actually moving dynamically. All right, so to summarize, I showed to you that these Rydberg atoms are really a great platform to study quantum simulation, because you can implement several interesting Hamiltonians, particularly of Ising and Heisenberg type, ordered or disordered. And I showed to you that there seems to be some interesting universal dynamics that you find of the system when you have a disordered system and you just look how this magnetization relaxes. And it's clear that it's beyond mean field. That is almost trivial, this statement, but there seems to be something universal going on here that we try to deeper understand and haven't done yet. But that's something for the theorists now, I guess. All right, this is the people working on this project here. This is the group in Heidelberg. I worked closely together with Shannon for a long time. He's now in Strasbourg. Adrien was a postdoc. He went back to Palaiseau. And we have very good collaboration here with the guys in the theory department in Heidelberg. Jürgen Berges Asia Pinheiro, he's now in Boulder, I think. And Martin, who was in Boulder, is now in Heidelberg again. So there's a good exchange here. Everything's different funding agencies. This is Heidelberg at night. Looks like a big city, but it is not. So thanks very much.
Yeah, thank you very much for this nice presentation. Any questions? Yeah.
So what is the definition of a spin glass? Does it depend just on J?
Yeah, the definition, as far as I understand it, is that you have a disordered system, yeah, that you have spin-spin interactions in the first place, and that you have some kind of slow dynamics. Usually the spin glasses are coupled to a temperature. They are at some kind of temperature. In our case, of course, this is to the best.
So can you change the dynamics by to be out of this the spin glass regime by changing J, by making it faster?
To a certain extent, that's what we did when we changed the density, because it changes the density, it changes the distribution of these J's.
Right.
Yeah. What we haven't explored so far is because we would have to go to different end states. I mean, first we want to write this up, but the next step would be now, for example, to look at different end states where the relation between this J perp and the J parallel gets different. That would be one of the things you would like to do. There's other things that we are currently thinking about. How could you possibly change this the ratio of the two J's? Is there ways that we can control the J's in some way? Yeah? And there's some ideas that we have. So what would be great is if we could, for example, turn off the J, easing J, and only have the dipolar, and then turn off the dipolar and only have the easing, and then study this dynamics. That's on the agenda, and we have some ideas, so it might be possible, I think. But we have to see whether it works in the experiment. On the paper it works. Should work, like always.
Other questions or remarks?
Matthias, have you thought of trying to do perhaps echo, echo experiment?
Yeah.
Have you?
Yeah, we can. We will. We just changed our microwave equipment. We bought some microwave equipment just last week. We got a very nice microwave generator. And we go for.
So perhaps you can discriminate the spatial asymmetries or anisotropies of the system.
Wait. What do you want to do with the echo? So tell me what you want to do.
Like hum echo, like in NMR.
Yeah, but here this is. Yeah. So why would you do that?
Well, if I understand correctly, the measurement when you do the pi over 2, it's somewhat similar to measuring the T2, right? The transversal.
Yeah, but it's not a T2 here. That's what I tried to allude in the last part. It's a pure, strong, I mean, what you create is very strong correlations. Of course, the question might be, typically use these echoes in order to get rid of some kind of, let's say, mean field effects or stuff like that. Here, the question would be, can we rephase the many-body evolution, yeah? That's an interesting question. We are thinking about these things indeed.
Okay.
Yeah. As I said, we just got the microwave generator.
Thank you.
And that's the first thing we are going to do, in fact. We are going to put an echo sequence. But there's more. I mean, we can learn a lot from the guys in NMR. They have lots of crazy sequences that I never understand, but they seem to work.
Yeah, let me ask you a question. I mean, do you think it would make sense to try to, if at all experimentally possible, to go off from disorder a little bit and to introduce gradually some symmetry, some structure into the system?
I mean, on the paper, that's what we did when we increased the density in the simulations. In the experiment, that's one of the things we should go for. Yeah? We could do this by changing n and things like that, so that the blockade plays a larger role, and that is exactly what probably you were asking for.
Yeah,
so that we could go more into a system that is governed by these two-body correlations.
Or by making an underlying optical lattice, which
Yeah.
kind of pins particle a little bit.
Yeah, we could go 1D. We could try to. What we have is we just got a nice spatial light modulator. So with this, you could modulate the excitation light and get some order in the system. Yeah.
And for theory, it would be easy to include that, isn't it? And they could do simulations ahead to see whether there's anything striking happening.
I think there's no theory available. I mean, the theory that we do so far is these truncated Wigner
Yeah,
approximation.
the Macy and the...
Yeah, you could do the maze, but you see maze is a finite cluster, and on the timescales that we are, maybe I should mention that these timescales that we have correspond already to more or less 30 inverse interactions times. And that is where the correlations should have already propagated out of these clusters that you build. So maze should eventually fail, in particular when it comes to looking at correlations. So one of the reasons why we want to look for susceptibilities is that if you just measure magnetizations, that's what we can measure at the moment, then these methods seem to work fine. But if you look at higher order correlation functions like susceptibilities, they will get trouble. And so on the one hand side, this maze will no longer capture long-term correlations because the correlations go beyond your cluster size. The truncated Wigner approximation will fail because it's not tracking enough of correlations, because you only start with initial fluctuations and you no longer have the build-up of correlations through the Hamiltonian dynamics subsequently. So I don't think that this is why I'm usually reluctant to use the term quantum simulation, but here I feel somehow like that might be something that could be considered quantum simulation. Let me put it this way, very cautious.
So
but
challenging theory. Okay. You still. So if there's no more questions, then we have a coffee break now. First of all, let's thank Matthias once again. And we're a little delayed, so let's reconvene at 3:30. First speaker is Kajo Levenkopf, and he will be not talking about cold atoms, but about spin Hall in disorder graphene, interplay between puddles and defect-induced magnetism. Please.
Hello. Well, first of all, I'd like to thank Hussein for inviting me. I'm learning quite a lot about a new subject for me, and I try to figure out my overlap with this crowd, and I think it's more like disorder and chaotic aspects. And with Hussein, I wrote a number of papers in chaos and disorder. So I'm talking about graphene today, which is a slightly different topic. Graphene got some prominence in this country due to funny reasons lately. And our president is very fond of this. So I hope at least we get some funding out of all this mess. So the talk today is basically here. The outline is I'll define the problem we're talking about. So I'll try to go, to be very pedagogical at the beginning, so I understand most of the people are not familiar with the subject. And then I'll talk about active spintronics in graphene, and then spin relaxation in different scenarios. Okay, so that's about this thing. So the idea is people are already on this road of spintronics for quite a while. So there has been lots of frustrations and success in developing some, let's say, working devices using the idea of creating dissipationless currents where you propagate spin instead of electrons. And nowadays you don't find yet in the shelves at the supermarket these things, but quite outstanding developments have been achieved in the last few years. So the key thing is to find good platforms, good materials to do the spintronics. And when graphene came, people thought about graphene as being an excellent candidate due to some of the features I'll describe next. So, but what is exactly I'm talking about? So the key role here is played by this spin Hall effect. And the idea is that if you have a system, some device, and depending on the nature of the material here, you can make current, electric current flow through this device, and actually while the electrons are moving, the two different species are separated, and then you can get strong spin polarizations and even spin textures at the edges of these materials. And the first really successful demonstrations of how good that is have been achieved 15 years ago, and all the thing is now how to make this into, understand this physics, and also how to make this work in different devices. So to understand this, the idea is that if you have if you define a spin current, basically you separate the two spin species, and the spin currents is the net spin flow flowing through your device, and you can divide, you can actually, by this means, you can actually define a conductivity, spin Hall conductivity, when you basically create a bias and you generate the spin current. And there is this figure of merit which is called a spin Hall angle, and basically it is the rate between the spin current or the spin Hall conductivity and the conventional conductivity. And nowadays, well, it began with something like 1%, 2%, and now people are quoting things which are relatively, the new materials, they are quoting figures which are significantly larger, like factors 2 or 3, where you can enhance this and keep still the conventional conductivity kind of large. Okay, so how does it come? The idea is that there are two, well, there are several reviews on that. There are two basic mechanisms, well, I'll actually stick to that, which is simpler to explain, and this skew scattering. And basically the idea is that is actually a theory by Mott, very old. And the idea is that you have a spin up, and the electron will be scattered by some atom which has a strong, for instance, a strong spin-orbit interaction. And depending on the spin-orbit interaction, the scattering is skewed. So there is a preference to go up, to go in this direction, sorry, if the spin is up, or if it is down, it go other way. And well, this is basic scattering theory, and the key ingredient is that the spin-orbit term breaks micro-reversibility. And so it will tend to throw a spin ups to one direction and to spin downs into the other. And in this way, you can get this polarized spin currents. So the idea is then what kind of materials can do that? And now I'll come to my transparency on graphene. And for those who never heard about this material, it's basically graphene is I mean, you have carbon atoms in 2D. It's a single sheet in this case, and they have this two triangular lattice. They have this honeycomb lattice here. And basically, I make this color code red and blue because the unit cell is constituted of two atoms, although they are the same, two carbon atoms. And the simplest model that describes the low excitations of graphene is, you can write in this way. Oh, there's a T missing here, which gives the energy scale. But basically, it tells you that an electron at the B side can be annihilated and can jump to the if you're in the blue, you can jump to the red, and if you're in the red, you can jump to the blue. And this is the effective Hamiltonian. The simplest effective Hamiltonian describes the low energy spectrum of graphene. So, and if you do the math, you basically, I mean, the dispersion relation is something like that in 2D. This is Kx and Ky. And close to the charge neutrality point, you have this linear dispersion. And so you can actually write this Hamiltonian in K space in terms of something like a Dirac Hamiltonian, if you wish, with a very low speed of light. And this is the key ingredient for graphene. So where this sigma here is not the spin, this sigma is a pseudospin, which refers to the two species or two sublattices in graphene, and that's about. And then the first thing is, well, you have electrons which behave like massless electrons. These are excitations. This is due to the fact that you have this underlying lattice here. And this has been measured, this dispersion relation, this is genuine. And due to this linear dispersion, due to these massless electrons here, there are a plethora of new phenomena that come up in transport, in excitations, also in optomechanic applications, et cetera, et cetera. So, and now the issue is, why is graphene good for spintronics? So this is a talk about spintronics. And so if, for the ones that remember the lectures in condensed matter, so if you take the atom, if you think about carbon atoms, it has a small z, so the spin orbit term is very small. And so it's expected that the spin orbit coupling in graphene should be extremely weak. So in this sense, everything I told you before of the ways you generate this, kind of spin current won't be generated in pristine graphene. You have to do something to make it work.
Sorry, you confused me because
Sorry,
before
yeah.
I thought your spin orbit involved a linear momentum operator, but now it looks like an ordinary L dot S.
Yeah, so this is in addition. Yeah, so, sorry, yeah, okay. Let's go back. That should be clear now. Okay, so this is the simplest model of graphene you can possibly envisage, right? And this, as you mentioned correctly, this sigma here is not really, it's a pseudo-angular momentum, or pseudo-spin. And this is the zero order kind of Hamiltonian you have to describe graphene. Now, if you go to, if you want to describe additional effects, then you have to remember that graphene is constituted of carbon atoms. And then carbon atoms have a spin orbit, and that comes in addition to that, okay? So, okay. Please interrupt me, because if I lose you, then the whole exercise is pointless. And so the first idea is, and then people thought, okay, good. So if I cannot do active spintronics in graphene because I cannot bend the polarized currents, at least since graphene has such a small spin orbit coupling, then I can propagate spin species for a very, very long lengths or very long times. And this will be an excellent material to transport spin without spoiling the properties that I wish. So this is what I call, or people call, passive spintronics. And the first efforts, I mean, back in 2010, 2015, was to establish how long can you have the spin diffusion in graphene before the spins flip due to interactions with spin orbit or other kind of impurities, magnetic impurities of the material or the surroundings. And so this is a pretty large number, actually. So people have achieved very excellent numbers here, figures of merit. And so this was one of the ideas of how to use graphene to transport electrons. Okay, so, but there is the other thing, which is the active spin orbit. How can I bend the spin trajectories? And this is a nice, very nice story, because these two guys, Ken and Meili, they thought, well, so I use this language, I mean, this funny dispersion relation of graphene, and suppose that I have this spin orbit coupling. Instead of having this nice conic dispersion relation, if I add this by hand, I can, I mean, there are theories, they can calculate the spin, the dispersion relation, and they found this very funny states here. There is an opening of a gap, there are these states, and the states, they found that they were very robust against disorder. And so that's the magic. So they proposed that you can have a very strong quantum spin Hall effect in graphene if this spin orbit was sufficiently large. unfortunately, they actually used a coupling constant which was too large by all means. I mean, that was very unrealistic. But this paper was the birth of a field which is called topological insulators. So although they were right in the numbers, they were right in the physics, and people understood that very quickly, and they started to work with other materials where you will have this band inversion, this surface states, this protection to explore this physics in a totally different scenario, so not graphene. No? And you probably heard that this is a very conceptual new thing in condensed matter, and there are lots of things happening in this field. So the big thing here is that this funny states that propagate at the edges of the material. They have some spin texture, and they are very robust. Now the issue is, can we actually do something to graphene, change it artificially or dope it in order to get back this phenomena predicted by Kane-Meli? And this is what we call active spintronics. And this is the, I mean, now that's the introduction, and this is the first paper I want to mention. And so what people understood early in the game is that if you dope graphene with heavier add atoms with a large spin orbit coupling, even if they are disordered, you cannot place it regularly there, you can make this magic work, and you can generate, by engineering this spin orbit and the add atoms, you can engineer this band crossing and this topological insulators in graphene. So, and starting from these early proposals, people did some better jobs into finding different materials and cheaper and lighter materials that will actually distort the graphene lattice. So there are hundreds of papers on that. And eventually people actually have made some experiments. And these experiments are quite beautiful because the idea is, I'm sorry this is very small, but it's actually a theoretical view of a picture of what's going on. So these experiments, essentially, you put the source and drain bias here, and the electrons will flow through this hall bar to this bar of graphene. And if you have sufficiently, if you dope sufficiently this bar with elements that will make this spin orbit, enhance the spin orbit coupling, then what happens is that different spin species will eventually flow to different sides, and you have some no local resistance. I mean, this current here will bend, for instance, spin down, and will eventually come out here. And this has been measured. And the result is basically that, well, this is a diffusive system, so even in the absence of spin orbit, there is always some little current that flows here. So this is this blue sign, the blue curve. And if you dope the system, or if you hydrogenate or do other kind of things, then you get this red one. And depending on the percentage of doping, you have a larger and larger sign of this no local resistance. And this is a proof that that electrons will eventually polarize and end up in a different terminal. Okay? So, and then the question is this related to this quantum spin Hall? Is this related to this nice physics predicted by Kane-Meli? How can we explain this no local resistance? And this was the first paper we wrote in that respect. And then we basically made some simulations by putting these guys randomly, putting these add atoms here. And then we actually wrote a code to compute this no local resistance by computing Green's functions and standard techniques for transport. And well, this is with a postdoc of mine, and we actually developed a new code to compute this multi-probe transmission or conductance through this to any kind of shape of device. And what we find is that by randomly doping a graphene Hall bar with, varying the doping, then we start with something that actually is not really polarized. It flows like here. And there is some critical value of the doping where you actually have almost like unitary transmission to the side. So this is the quantum spin Hall limit. And this is probably what people measure because it's not perfect. And here this is a too low of a concentration. And so this is, these are our predictions for the experiment. And we read the concentration of the impurities, and we have some let's say, some theory that well, we know, like, there is some uncertainty with respect to the concentration of impurities, but other than that, this is the result. So, sure, please. Not really. This is still, this is diffusive. So that's a good question, because if you go to, okay, so if you go all the way to the topological phase, and you have this protection of states, then you stick to this state and you propagate ballistically, okay? So if you have a full developed topological phase. If you don't, then you are propagating in a very disordered system. And then there is this crossover from being diffusive to ballistic, right? It was in the, but the Landauer-Büttiker formalism is let's say, it's elastic scattering, but if you make the system sufficiently large, you can address also a diffusive regime. It's not practical. It's not the smartest thing to do, but in order to simulate that, in order to simulate the geometry, you have to, unfortunately, do a calculation like that. So if provided the system is sufficiently large, you can address a ballistic, diffusive regime also in the Landauer-Büttiker regime.
I have a question too.
Sure.
This Rashba, is this 2D Rashba symmetric, like sigma x
Yeah.
dx plus sigma y dy?
Exactly. So the idea is that, I mean, there are several competing mechanisms depending on the realism that you address the question. So the thing is that if you have only this add atoms, you have only to worry about spin orbit. Now, if you want to address really what's going on in the experiment, the graphene is actually deposited over, for instance, silicon dioxide or HBN, so there is a substrate. This substrate breaks the inversion symmetry, and then you generate some Rashba term. And that has to be in their calculation.
So it wouldn't work with Dresselhaus?
Dresselhaus is also there, but has some different origin. Rashba is exactly this, that you break this inversion symmetry. Dresselhaus has some different microscopic origin. So, and it's not that you can really rule out, but it's smaller, expected to be smaller here. So in this sense, what we can do is that we understand that the spin orbit works. We don't understand, but we are not yet in the quantum spin Hall effect, and that's the next talk, next thing. Oh, sorry. Before we do that, yeah. So and then I'll just speak about the specific spintronics before I move to the quantum spin Hall. So as I mentioned before, people have achieved, without doping, without impurities, they have achieved a very, very long spin diffusive lengths or times. And well, from the experimental point, this is very, very reassuring. But if you compute in any realistic kind of, or in any kind of simple-minded theory, what should be the spin relaxation time for graphene, pristine graphene, you get something, figures of merit of about 1 microsecond. And if you do the math, then you should expect that the electrons will propagate for a much, much longer length before they flip. And so these guys here, they collected all the data in 2012, and they basically came up with this discrepancy. And that was the status of the theory and experiment in 2012. So this is what's called the puzzle, the embarrassing puzzle, 10 to the 4 discrepancy. This is not a small problem. So, and then that motivated several people to try to understand what kind of extra mechanisms could actually cause this discrepancy. And well, we came up with some theory. So let's rush. So there are several experiments that show that. And we came up with some theory, which was basically the spin relaxation due to extrinsic, let's say, impurities. And basically, if you do the simplest thing you can ever possibly imagine, Fermi-Golden rule, then you can write this spin relaxation in terms of some mechanism that does some spin flip. You have the density of states, and you have the concentration of disorder. This is the simplest thing you can actually imagine. The problem is, and that's the puzzle also, that experimentalists, they will see more or less the same spin relaxation time regardless of the doping. And as we saw, the density of states of graphene close to the charge neutrality point goes to 0. So that means that if you take this Fermi-Golden rule, right? So when the density of states goes to 0, this time blows up, right? So that there is something really, really fishy going on here. And so our theory was going to, I mean, we set up a scheme to try to understand using some realistic model for that and to try to understand what's going on here. And that was basically the title of my talk, that we see that graphene also is kind of very irregular. So once you put the sheet of graphene over a substrate, there are different regions which have different dopings. And so it's very unlike, although you have a situation of a charge neutrality point, locally you always are somewhere away from 0 density of states. And if you include that ingredient, taking, for instance, what the experimentalists measure, so if you compute, I mean, this is what people measure for the local density of states at charge neutrality point, and if you put that, and you cook up some mechanism for instance, vacancy and local moments, then actually for reasonably concentrations of doping, you get figures which are consistent with experiments at the charge neutrality point. So this is basically vacancies, they generate local moments, and here you have a kind of standard Anderson model where you do some rotation, Schrieffer-Wolff, and all technical things, and you end up with the right numbers. So, and this is the passive. So, so the bottom line is that, the bottom line is that once you have this decorated graphene, then, the bottom line is that once you use this realistic modeling for all sorts of disorder, then you get the right number. So how, then the issue is, how can you improve on that? And how to improve on that is to change the substrate. And this is what the experimentalists are doing now. So let's go back to active spintronics. And so if you have this decorated graphene with add atoms, we saw that in some regime you don't have the quantum spin Hall, but you have some sort of diffusion. And people were looking for the quantum spin Hall phase, and apparently the experimentalists have a hard time finding it. And that's what the last topic is, how can you explain the absence of a topological gap in this kind of systems. And so, just to remind you, if you have this quantum spin Hall, as I told you, there is a regime of doping where you have a quantized resistance, and it's extremely protected. So no matter how much disorder you put in there, this guy is one. And experiment by varying, for instance, the doping, you should see a constant sign, and that has been seen yet. So the issue is how can you explain that? And what we understand is that what is detrimental to topological insulators if you break time reversal symmetry, if you have some magnetic impurities. And is there a way to understand how you have magnetic impurities in this system? And this is what we are going to show. And so there was this PRL early this year, which was competing with us. And these guys actually put forward a model, which is a kind of Kane-Melley, these guys that invented the new version of topological insulators. This is this term of the Hamiltonian. And there is also a term which is due to electron-electron interactions, and it's a kind of a Hubbard term, okay? And this is justified by different ways by ab initio calculations and other groups. So this term is there, okay? And if you do a mean field, then this is a very simple thing. Then eventually, depending on the strength of the interaction and the strength of this hopping term, there is a competition. Then you have some local magnetization, and eventually these local moments will break time reversal symmetry, and you despoil all the fun of having a topological insulator. And so in order to treat that, we developed the whole machinery to calculate transport in that, so it's a self-consistent Green's function approach. This is not really important. But, and then we reproduce part of the results of this group. And it's very interesting because they showed that as a function of doping, so this is varying the chemical potential, you have this perfect channels where you have quantum spin Hall, the topological phase, and then in these 2 points, you destroy them by creating these local moments. And we addressed, for instance, just to show you how it happens, we addressed this point A, B, and C just to see, get some insight. This vacancy here will generate a local moment, and what happens in the transport is something like that. So point A, just to remind you, sorry, is where you have perfect transmission, okay? And so if you start with electrons at this site and you make them flow, then if you have this configuration A, then the electrons will actually flow all the way through, no problem. And also here, there is the vacancy here, but the vacancy is not sufficient. I mean, the energy is such that you don't form a local moment. Electrons flowing at the bottom of a line of the other edge of your system also will flow through. The situation B is just, oops, sorry. Situation B is just, oh, I'm making a fool of myself here. So this is almost when you break entirely the time reversal symmetry. And here is this extreme case. So let's address this extreme case, the C. So the situation C is that you have electrons flowing from this side, and there is no obstacle, so they flow all the way through. This is a quantized resistance, if you like. And the electrons of the other spin species that flow in this side, they hit this magnetic moment, they flip spin entirely, and they flow backwards. So in the net result is that here you have a conductance, 2 channels for going from one side to the other, and here you just have 1 channel, because this one, all the electrons that come here, they are back reflected to the other side. And so this is the mechanism where people explain this absence of or the breakdown of this topological phase in graphene. But unfortunately, and that's the interesting part, here is where we come, this mechanism is only effective at 2 points. And so if I'm an experimentalist and I swap through all this region, I will see a topological phase here all the way. Here probably I have more difficulty because eventually I excite more channels, and the breakdown only at 2 very tiny or 2 very narrow windows. And this is not what is seen. People actually don't see this topological phase all the way through. And so this is our contribution. We have to look at after other mechanisms for local-induced magnetic moments, and we actually understand that this is due to edge disorder. And so this is our calculation. So we start with a very simple-minded model where, for instance, these edges are not perfect. They are just rough. And depending on how large is this wedge, then you have almost a perfect transmission here of 2. But as you increase the length of this wedge, then you jump from the situation of a topological phase to this. So remind you that we introduce disorder just in one side. If you would introduce disorder in both sides, this is just a theoretical tool just to play around to begin with, then you also destroy this perfect conductance here. This is just to show that introducing disorder here, you basically go from a situation of 2 channels to 1. And obviously this is a very pathological kind of disorder, so we play around with different scenarios where you just start extracting atoms at random, but the idea is that these edges, they are created by lithography, so they are very rough. And what we find is that as long as you have a sequence of 5 atoms forming a zigzag, then you have spin polarization at the edges, and you see exactly the effect that I described before. And so, and this extends over the whole range of chemical potentials where you have the topological gap. So, so in this way, we believe that we have found a mechanism to explain, due to edge roughness, which is well established by experimentalists, that it's always present, that explains the suppression of quantum spin halls. So the thing is how to circumvent that, and people have already in the last few years developed other strategies of synthesizing these ribbons, and basically chemistry. And the problem is that basically they grow that perfect nanoribbons in copper and other materials which are conducting. And so when they separate the graphene from copper, they have problems by destroying graphene. So, but I believe that in the next future, you will be able to also grow these nanoribbons in insulating substrates, and then we probably hear more about this quantum spin hall in graphene. So, and just to conclude, just a little bit, or sort of outside of the topic here, I'm very excited with this paper that we just finished. And to give you an overview of what is all this stuff on topology, is that all these ideas that have been developed in the last 10 years about topological insulators, invariants, et cetera, they heavily rely on some kind of integration of one observable or one, let's say, curvature or an object over the Brillouin zone. So that's the key thing. Now, people working with topology, they say that basically having these invariants, you have something which is robust against disorder. So the issue is then, the question is then, this is a very daring statement, because if you have disorder, it doesn't make sense to speak about Brillouin zone at all, right? And so how, in which, is it, the statement is valid in perturbation theory, is valid all the way through, or how can we interpret that, right? If you start at the other side with an amorphous system, you don't have anything to integrate over the Brillouin zone. How can you decide that this guy can be a topological insulator or not? And so this is this new development on trying to understand strong disorder topological insulators. And so this is a kind of a thing that we are after. So integration over Brillouin zone is not good. So you have to formulate everything either in terms of Green's functions or other object. And last year, actually 2 years ago now, some people came up with a toy model where they show that a random amorphous system that has some, let's say, conditions of on the dispersion, local dispersion relation, show this quantization of the conductance, show edged states, and has nothing to do with let's say, Brillouin zone integration. And now but this is a toy model, and we came up with a system which is a realistic system, amorphous bismuthine that you can grow, and hopefully grow here in Brazil, and that we believe that will have the same, let's say, properties of this toy model, and then you see, let's say, we are moving towards seeing a topological insulator in amorphous systems. And I guess that the challenge now is to understand better what kind of invariants you can build to explain that, and what kind of physics is underneath these systems, approaching from the other side, from the strong disordered side, and not from the perfectly clean. So, I spoke already quite a bit. The conclusions is that experiments report a strong spin Hall effect, not quantum, but spin Hall effect in graphene, depending on atom concentration, which is responsible for spin-orbit coupling. And we are able to describe this physics by treating correctly atoms that form local moments, which are detrimental to transport, to quantum spin Hall. And this spin-orbit coupling is expected to induce quantum spin Hall effect, and it has not been experimentally observed yet. And we put forward some mechanism based on electron-electron interactions that change the standard picture and explain these experiments. And we hopefully see new experiments exploring proximity induced by changing spin orbit, by changing substrate, and these guys will be probably the new way to produce quantum spin Hall in all sorts of 2D materials. So thank you very much.
Yeah, thank you very much for sharing these insights into this very topical problem. Are there questions? Chris?
Okay, first naive question is, I think of all spins as quantum. So how can a spin Hall effect not be quantum?
Quantum in the same way as quantum Hall, right? So you have Hall conductivity in normal materials, but the conductance is not quantized. And here the quantum spin Hall is, spin Hall is where you have spin currents flowing through your material. And quantum spin Hall is that this spin currents, they are quantized in the sense that you have a spin quantum in one side and the other side. So that's terminology.
Oh, okay, then the second naive question is, I'm trying to visualize what's really happening at a microscopic level. Are charges really moving, colliding, exchanging spin, and that's how the spin is going around? Or is just this spin on this side interacting, making this spin on this side move, and then there's like a spin wave going through the material? Is there physical motion of particles in spin currents?
So
is that an essential part?
Sorry. Yeah, it's an essential part. So let's go back to the beginning, and this nice insight by Mott. It's one of the mechanisms here. So the idea is that if you write the T matrix, right, and you include this spin orbit term, and you sandwich the T matrix in let's say you take either this term to be simple, first order Born, and you include and you write some sort of rate of scattering rate, and basically what you find is that you break this micro-reversibility. So electrons that hit this spin, this disorder or this atom, they have the if you are spin up, they have the preference to go, for instance, left hand. Or if they hit spin down, they go more like right hand. So if you ask me to do the math now, I hurt myself because I forgot. But it's a simple thing. If you know what to do, you do in 5 minutes. If you don't know, you take you half an hour and you figure out. So it's a simple thing. Okay.
So spin currents are always accompanied by real currents.
Yeah. In this case, the idea is, okay, so this is a more subtle thing. Good question. So the ideal situation, which is not simple to achieve, is that you have electron currents flowing both sides. And so you have a net zero current, but there is motion. Zero electron current, but there is motion. So there are electrons flowing one way and the other way. But the electrons flowing this way are, for instance, spin up, and the other guys are spin down. So, and that balance is sometimes hard to achieve. But the idea is that if you do that, naively thinking, the currents, they basically, if you have elastic scattering between, not many, very few electron phonon or electron, so basically elastic scattering, the dissipation will occur at the reservoirs. And if you have the same amount of current flowing outside one reservoir entering, so the dissipation is not necessary at zero bias. And so you have a situation, ideal situation, where you have a very little dissipation and a transmission of spin, but not of electrons, net transmission of spin. That's the idea. Okay?
Other questions? Yeah, sure.
So I think the spintronics is promoted as like having advantages over normal electronics. Is this because it takes less voltage, or there's less energy dissipation with spintronics? What's the advantage?
So there are two main things, which are the two main promises. One is what you said, is that you have less, in these circuits which are extremely small, and now we are facing this issue of having to dissipate all this heat. So having less dissipation is important. The second thing is that they will transmit a different thing, like they will transmit spins and not electrons. So you do, the whole information processing is entirely different. So you do in a different degree of freedom. How you do it exactly, that's another thing. But you have at your disposal a different bit of information, if you wish. And so, although it sounds a little bit far-fetched, so there are some applications already in memory tracks and things that are, there are lots of things going on in spintronics which are not ultimately related to transport, like I told you here, but there are things which are more related to information than to electronics or to currents.
Can you briefly comment on how you combine the recursive Green's function technique with your Hubbard type interaction?
Oh, yes, okay. So you took the most crowded view graph of my presentation, which I jumped very fast through. but that took a long time to get it work, and so we are very proud of it, although I flashed it through, very fast. So this is the work of a postdoc of mine who is now hired in a university in Rio, Leandro Lima. So we use type binding, but that's not important. You can use density functional theory. But the thing is that you treat interactions at the mean field level. So that's the restriction. And then basically you have this Hamiltonian, and you write the Green's function at the mean field. So this is possible to write. And then you have to compute the occupations, which is very time-consuming. You have to do some nasty integration, and then you do a loop. When you do that, you have you can have a bias. You have to integrate over the complex plane, etc., etc. But you have to crank that because it's an open system, right? It's different than standard Hartree-Fock, where you do things in like diagonalize a matrix. Here you have a open system, you have a bias, it's out of equilibrium, so you have to find the voltage drop, all that stuff in this loop. And basically, once you achieve convergence, then you can compute all kinds of currents, et cetera, et cetera. The Green's function, this recursive Green's function is just, let's say, a strategy how you solve the Green's function for very large systems. So basically, for transport, you don't need the information about all sites. You just need the information about entrance and exit, because this is what you are interested in. And so this is a trick or a technique that explores the fact that you don't want to have the information about the full Green's function matrix, but just of some sectors. And this is a very efficient technique. We contributed to the development, but the idea is quite old already.
Okay. Maybe one very brief one from the end. Yeah. Is there topological invariance for these amorphous or strongly disordered systems known?
There are speculations. So there is one which is called bot index, which the idea is kind of convoluted, and that's
yeah. The bot index comes from the quasi-crystal type setups. Yeah.
But the thing is this. So if I start with the standard theory, right? Yeah. I can write, and it's not my work, but people have figured out how to write this this integral in terms of Green's functions. Okay. Where you don't integrate over the Brillouin zone, but over the frequencies. And so if you believe in this, and you believe that the extension to Green's functions is fine, no matter if you have, or not, if you have disorder, then basically by writing this Green's function, you get some topological invariant, even for amorphous system. So the key issue is to prove that this assumption makes sense, right? So it works for pristine systems, but why should it work for very complicated beasts? And then, but then you can show that by the end of your calculation, what you get using this Green's function is exactly the same as the bot index. Okay. So and here is where we are. So we know pieces, and it works, but we actually don't have the full bridge constructed. And that's the fascinating thing about the current situation in strongly topological insulators. So that's the idea.
Thank you very much. So let's think
Okay,
again.
thank you.
So there's one more talk. According to my list. It's not on the desktop. Yeah? Okay, great. So our final talk will be given by Marcello Yamashita, and he will be talking about dimensional effects in Efimov physics.
Okay. Thank you very much for the invitation. Thank you very much, Hussein, for the invitation. I don't know how familiar you are with Efimov physics, so I will spend some slides just to put everybody in the picture of Efimov physics. And let's start with some a story about the Efimov effect. And this was the paper from Vitaly Efimov in 1970, where he just studied these three spinless neutral particles of equal mass interact through a potential GVR. And at certain point here, G is smaller than G naught. The system, the two-body system is unbound, and here G larger than G naught. This you have a two-body bound state. So what he observed is a very interesting aspect of the two-body system. When you are here exactly at G equal G naught, where E2 is equal 0, then you have an infinite number of three-body bound states. So this is a bit counterintuitive. And here in a pictorial slide, if you have for a finite two-body energy, you have a certain number of three-body bound states. Then if you just decrease the magnitude of your two-body binding energy, what happens is that the number of three-body bound states increases. This is a bit counterintuitive. And you can start to play this game until you want, until E2 exactly equals 0. Then you have the appearance of such an interesting effective potential proportional to minus 1 over rho square, which is the hyperradius of your three-body system. Then you have an infinity three-body bound state. This is very interesting if you just remember from Landau Lifshitz quantum mechanical books. There is a section which he discussed this fall to the center problem. So this is quite an interesting potential, and the ratio of this between two consecutive states is given by this interesting factor for three equal mass bosons is 515, is given by this exponential 2 pi over s. S this is the discrete Efimov scaling factor, which depends on the dimension and on the mass ratio of the system you are treating on. And also the root mean square hyperradius ratio between two consecutive states is given by this square root of this factor is just 22.7 for three equal mass bosons. So the picture you may have in mind is just Matryoshka's Russian nesting doll, which have a fixed proportion between one and the next one. So now we know that this kind of Efimov effect is a kind of paradigm in atomic and nuclear physics, and it's an area we call now Efimov physics. And you know that the number of physical scale dominating the physics is quite small. So the system is described by only here 2 and 3 body observables. So once you can just produce the same low energy observables, we obtain results which are independent of the potential. So it can be a direct delta potential, Gaussian potential, square L, and this is what we know by universality. So universality is mainly contained in such a picture, which is it's a hybrid picture of Albert Einstein and Marilyn Monroe. If you just if you are far from this picture, you are not seeing Albert Einstein. You are seeing Marilyn Monroe. But you can have exactly the same effect if you just decrease the size of this picture. Then we have the Marilyn Monroe. It's a superposition of one very detailed picture of Albert Einstein with the less detailed picture of Marilyn Monroe. So it's a question, universality is basically a question of resolution you have in your system. So just let's say that R0 is the distance between pixels and A is the distance of an observer. And then the universal limit is just achieved here with the Marilyn Monroe limit when these ratios is obtained. It doesn't matter if you are far away or if you just decrease the size of your picture, exactly the same effect is achieved. So it depends only on the ratio. So just changing this quantity to physical language, then you have the range of the potential and the two-body scattering length. So if your system are large enough, then it doesn't matter the shape of the potential at short distance, that your system will not feel what's the difference. So this is the essence of universality. So what I'm interested here in Efimov physics is this universal Marilyn Monroe regime. It's this two-body scattering length must be greater than the range of the potential. So to describe Efimov state, here we are talking about only 3-body states. Then only few scales should be enough. Then I can choose as a scale the two-body scale. Two-body scale can be the two-body scattering length or the two-body energy. For shallow two-body bound state, it is just given by a proportion here between E2 and the two-body scattering length. And it can be another scale, a 3-body scale. It can be the 3-body energy. Then any 3-body observable can be described at certain energy E. It can be described by a universal scaling function, a dimensionless scaling function given this observable by this quantity E3 to the power eta. Okay, and the Efimov states was discovered for the first time experimentally in 2006, and it was measured inside ultra-cold atomic traps, and it was measured by a 3-body recombination loss here at these points, at the points where the 3-body bound state turns into a resonance. Then you have a resonance here at this point, and then the 3 atoms recombine in 2+1 in 2 with a deep bound state with due to the large kinetic energy. Then you have the loss of these atoms at this point, and this they can measure the scattering length, then the ratio of this, the position of the ground and the excited state, and see that they are really the Efimov states. But this was produced artificially by using the tuning the two-body interaction was fetched by resonance. But the question is, can they exist, they were artificially produced here, and can we find them in nature? And the answer is yes, and this was the observation of the Efimov states of the helium trimer in 2015. And this is an interesting experiment made by the group of Reinhard Donner. And this, you have a cloud of atoms, then you just pass the beam through diffraction and separate monomers, dimers, and trimers. Then you explode the cloud, and then you see you can reconstruct the energy by inverse kinematic, by reconstruct the kinematic equations and see how is the energy. And they could measure the ground state and the first excited state of this helium trimer. So this was an introduction, and this is what I'm interested to study. And we know that the occurrence of Efimov effect happens here in 3D, in a three-dimensional cloud, but it does not happen here in 2D. It does not happen. But we know what happens here in between of 3D and 2D, because it's not an abrupt change when you start to compress your ultra-cold cloud in one direction. It is not immediately 2D. Well, so my question is, what happens with the Efimov state when you are here in between 2D and 3D? And I found only one work by this group of Aarhus group from Jensen, Garrido, Fedorov, and Nielsen, that for 3 identical bosons, they found a fractional dimension for the existence of Efimov state. It happens for 2.3 to 3.8 for 3 identical bosons. So they used some hyperspherical method to calculate such dimension. And then I would like to study this problem with zero-hand interactions. And this was done with this is my PhD student, Derek Rosa, together with Tobias Frederico and Gaston Krain. And we found a simple way to extend such a dimensional interval for the existence of Efimov states. So let's just consider a three-body state with zero-hand interaction, and then it can be described by two-coupled integral equation for the spectator functions. So if you just put the two-body energy, which is inside here, the two-body amplitude, you just recover the three-body binding energy, three-body binding Efimov energies. And this generalize, we just put a D, an integral in D dimension, here to generalize the Korniakov and Termartirosyan equations. And here we have the two-body amplitudes given in an integral with D dimension. Here is not very complicated, but we have a problem here because you have scales. We have the two-body energy, and there you have three-body energy. But just let me remember that Efimov properties are determined by large momenta. And this was given by Danilov in a paper 10 years before the paper from Vitaly Efimov. And just take the large momenta, and in this limit, all scales are set equals 0. We are in a very ideal regime, and we don't have any scale. And then, if you just remove the E3 and E2 here, you just can calculate closed form for the two-body amplitudes. It's given in a very simple form with gamma functions, which can be easily solved in mathematics, for example. And then I need to calculate Efimov states. I need another ingredient, is that in the ultraviolet limit, the integral equations are invariant under a scale transformation. So solutions for Q or Q and lambda Q, each solution of Q and lambda Q is also a solution. So this form of solution is the invariant under a scale transformation, and it is also given by Danilov. And this gives our log periodic solution from Efimov system, from Efimov states, and it gives the infinite three-body bound Efimov states. So just last, insert these ansatz and solve the characteristic equations for the Efimov three-body, for that three-body bound state equations. And then we see that S, that discrete Efimov scale, comes from the solution of the following transcendental equation. F is just given this form of gamma functions, and these integrals do not depend on the dimension you are considering, and then you just put the mass ratio of your system. And what we found here is this is a band where the Efimov state exists as a function of the mass ratio of the system. So we just can recover for A equal 1 for 3 identical bosons the result from Nielsen, but we extend for another mass ratios. We know that it's much easier for experimentalists to measure such a Efimov state if you are in a heteronuclear system, because the ratio between the energy and excited states, it decreases when you are in an asymmetrical case. So we can just extend the ratio. This is the square of this is the ratio between the binding energies. And here is the ratio between root mean square radius of a system and the next one, the excited state. And as a function of this mass ratio of the system and the dimension of the system. And you see, if you are here, the black curve is the 3D situation. And you see, for any dimension, if you are A equal 1, you are in the worst case for experimentalists to observe such a Efimov state. Because the ratio between energies or root mean square radii or the scattering length is a maximum. So this is a very easy way to extend such Efimov physics for d dimension. So when you start to compress your cloud, you just decrease, and it's not immediately 2D. It's 3D, and it starts to be a fractional dimension, then it reaches the 2D regime. But this first approach does not explain why the Efimov state appears or disappears. And then we start to calculate this three-body system, the Born-Oppenheimer approach, just to understand why the Efimov states disappear when we are approaching the 2D limit. So here we will not be in very ideal case with no scale, but here we are treating with finite energies, but with have light system. So let's start here, and we calculate here in the configuration space. We can just separate the movement as usual in the Born-Oppenheimer approximation, and then we write the Schrödinger equation for the light particle and for the heavy particle. And here, what enters here is a Laplacian in d dimension. So this equation we are calculating d dimension. And from the light particle equation, it comes the effective potential which generates the Efimov effect here. So let's first calculate the light particle equation. And for a zero-hand potential, the solution of the light particle equation returns this effective potential in d dimensions. So you can just follow when changing the dimension of your system. If you see that the potential when you change from d equal 2.1 to 3.97 and so on, and here is d equal 3, your potential starts to change. And this is written dimensionless effective potential, just normalized by E2, and here is the distance normalized by the two-body scattering length. So what happens is that when you are change the dimension, you are changing the potential. And here is a result from Fonseca, Rydberg, and Shanley, who deduced this potential, effective potential in 1979 for d equal 3. Our results recover such a result from Fonseca, Rydberg, and Shanley, and the Efimov behavior is basically given by this shorthand behavior here, 1 over r squared, which is, and let's see with our limit of our effective potential for large distance is just to recover the well-known results for d equal 2 and d equal 3. It's a Yukawa type potential, and d equal 2 is the potential given by this one. But the small distance regime is what returns you your Efimov physics. And if you just take the limit of r tending to 0, just recover this one is something, some factor which depends on the dimension of the system and also on the mass ratio of the system. But here we are in the Born-Oppenheimer approximation. But it's something over r squared, which gives you the Efimov effect. And if you just insert in the heavy particle equation the same solution, the same scale invariant solution, which returns you the log periodic solution here, and just you replace this r to delta, which is delta. If you just replace here, you recover that delta should be this equation, this 1/2 plus or minus is. S is the discrete Efimov factor. Then you know that if you want to have infinite solution for this equation, S should be real, and this should be positive. And if you just plot this d over 2, 1 here below, and this other term here above, you have a region where you have the Efimov effect. So this picture is just for the system lithium-6, cesium-cesium, which is a good, which fits the Born-Oppenheimer approximation. And then, if you see, this result shows a region where you have the Efimov effect. So if you start from 3, okay, in principle, I don't know how to go to higher dimensions, but you start from 3, you just reach a point where this term becomes real and is not imaginary, not anymore, and you don't have more Efimov effect anymore. And then you can just recover the three-body energy spectrum for finite E2 and just replacing that effective potential here in the heavy particle equation. And then you can just write in terms of a scaling function. Here, given in this form, here was first written in this paper. And you can just write here, I cannot recover individually the energies because all energies here are written in terms of E2. So it appears always as a ratio here. So I just chose to plot such energies as in the form of a dimensional scaling function. And here is the result for d equal 3. And here for E2, very close to 0, you have such Efimov ratio between energies. And when we start to increase the energy, the two-body energy, you are just going far away from the Efimov regime, and then the state just disappear in the two-body energy cut. So, I just understanding the first part, I showed you a very ideal case with no scales, and then I understood the region where the Efimov effect appears. And the second part is the reason why we have such an appearance and disappearance of the Efimov effect. And but this is the general situation where we can, in principle, use to study any mass ratio and with the finite scale, with finite energies. And for a general three-body system, we can just study the crossover from 3D, 2D, and 1D. What we did is just to quantize, to compactify one of the momentum. We just write one of the momentum in a discrete form, insert here a parameter which regulates your dimension. If you are, for R, large enough, then P is the, okay, you have Px, Py, and Pz. If R is large enough, you are in 3D regime. If you start to increase, to decrease R, you go to the 2D regime. Okay, so this is the form we usually change the dimension for a general system. So here is the Skorniakov and Termaterios equation for three identical particles. And then we just replace one of the integrals by a sum, which is given by this discrete momentum. So here's two-body amplitude and the three-body propagator. And what happens here, if you start here from large R, here you are in the 3D regime, and then we start to compress one of the directions of your ultra-cold cloud. What happens is, here is the more excited state, here's the ground state. Then start to compress your cloud one direction. What happens, the more excited state will start to disappear one by one. And then it remains only two states which are expected in the limit of 2D for three identical bosons. Then you have only two states. Here, if I change it not for three equal mass bosons, but for an AAB system, which would be easier to observe experimentally, which you can decrease the ratio of your energies. So the relation between the squeezing parameter and the oscillator length is just given by the simple form. Because in principle, in our model, when we just insert that discretization in the momentum, we have a periodic boundary condition. and the experimental is not easy to achieve periodic boundary conditions. So what we did is just to map putting the two-body system inside the harmonic oscillator and start to compress one of the directions, and then we map both situations, the E2 when squeezing one direction in the harmonic oscillator and squeezing with such a compactification method. So what we have is just simple form between the oscillator length and the compactification parameter. And what we have here is just the change from 3D to 2D. What happens here is that for dashed lines, E2 is fixed. And here for the solid lines, E2 is varying with the dimension when we are changing here by. So when you change from 3D to 2D, what happens is that the more excited states start to disappear when you are approaching 2D limit. And here is the result from 2D to 1D. You are just squeezing another direction. So we can, in principle, with our Fadeev equations in momentum space, with the one compactified dimension, extract the ratio of the three-body energy levels. So if you can extract the ratio of your three-body energy levels, we can, in principle, have the Efimov factor and the oscillator length. Okay, with S and BW, B omega, the oscillator length, and with S we can calculate which effective dimension your system are embedded. Here just put in our equation here, you have the mass ratio, you have the Efimov factor, and then you can make a curve with D as a function of your oscillator length. So in principle, experimentalists may be able, I don't know, we have some experimentalists here, but you can change your oscillator length and try to see what's the effective dimension of your system. Because you have something between in 3D and 2D. It's not exactly 3D, not exactly 2D, and something in between. What is this? Here is only a proposal. We don't know at this moment, in principle, how to directly measure such effective dimension. But this is a first guess how, in principle, you can try to measure it. Here is a result for lithium cesium. Okay, this is the summary of my presentation. We know that Efimov states just disappear one by one, starting from the higher excited states. And we could derive semi-analytically the dimensional interval where the Efimov effect exists for several mass ratios. And we show as a function of the effective potential which is responsible for the appearance of the Efimov effect. So the dimensional transitions can be made compactifying one or two directions. And here are some lecture notes from if you want to see how we make our calculations. And here are some review. This one was just published in Fadeev issue in Field-Body System about those results I'll show it to you. Okay, thank you very much.
Thank you very much. Are there questions? Chris?
Yeah, so you're considering a strict D, not like quasi 1D or quasi 2D. Have you looked at those scenarios?
Yes, it's this one.
Squeezing
It's the general D. It's not 1D, not 2D. It's a part of.
Right, but I mean, the more realistic experimental situation
Uh-huh.
will not be D equals 2.5 or 7. It will be maybe mostly a 2D or 1D system that's squeezed in the other directions. Have you looked at those types of more realistic experimental?
Yeah, but in my point of view, this is a realistic experiment because we are not, okay, it's quasi 2D or quasi 3D, for example. But the Efimov state will not disappear all at once. It will disappear one by one. And what I want to show is that you are not, okay, you are in something between in 2D or 3D. It's not 3D or not 2D. You have some states there which are in a, I don't know, maybe a fractional dimension.
To me, this is an unproven conjecture and a bit implausible.
Yeah, it looked like from your results that the relevant parameter was the ratio of the harmonic oscillator length to the scattering length. Is that true?
But I didn't understand.
The ratio of the harmonic oscillator length to the S-wave scattering length, that one.
This
yeah,
one?
Yeah,
Okay.
so it's that plot. That seems like the relevant plot, I guess. So that's how you would connect with an experiment. And that axis, that horizontal axis, is those units is really hard to attain experimentally. The typical, in a trap, a typical dimension is of order a micron or so, so about 20,000 Bohr. And a 3D scattering lengths, it would be difficult to get as large as 20,000 Bohr.
Okay, I understood, but here A3D is just a scale, just to write in a dimensionless quantity, this axis. In principle, you can start with a much bigger two-body scattering length in 3D and then start to squeeze.
Yeah, but experimentally, you're on that top right edge of that plot. Your harmonic oscillator length far exceeds the S-wave scattering length. Typically. Yeah.
Okay, but it's yes, for me it's strange because it's not 3D, because if you would like to calculate and you start to squeeze one of the directions, you will be in an environment which is not exactly 3D.
But this is all a question of scales. I mean, there's
in
scales
principle, your system will feel such a...
Yeah, but the question is, am I sensitive to 3 digits after the comma, or am I sensitive to only the first digit after the comma? So, of course, I will change something if I change my experiment, but it will be going from 3 to 2.999. So there's scales in every problem that you have in an experiment. There's scales, and here there's a natural scale, of course, and that's what you mentioned. That is the harmonic oscillator scale. There's another important scale, that is temperature. We haven't talked about temperature so far.
We didn't put
and there's a third scale, which is the van der Waals length. So there is, in this problem, there are several scales that are important, and in this problem, as I showed in my talk, there's even a fourth scale, and that is the scattering length between the cesium atoms that has to be considered. So it is not that you just change the geometry and you're changing dimensionality a priori.
But how we interpret the disappearance of Efimov state when we start to compress one of the directions?
Okay, maybe let me jump into this. I think there's a little bit of a misconception, Marcelo. This D that you are tuning is related with the number of degrees of freedom.
Yes.
And
yes.
evidently, there's no fractional number of degrees of freedom That's a purely mathematical abstraction. That exercise that the Daymark group has done, well, it's very interesting, but it's a mathematical curiosity. Squeezing a gas more in one direction than another, you still have, for each particle, 3 degrees of freedom. That's not going to change your Hamiltonian.
You are saying that's always 3. It's always 3. You are just suppressing the degrees of freedom in that direction.
You're not suppressing. You are limiting the range in which that degree of freedom can varies. Unless if you can really go strictly to
in our language, we are suppressing because you are just putting to infinity when you are compactifying one of the moments.
In the case of yes, in confined symmetries, for instance, if you have in one direction a stronger confinement than the other, consider the other 2 dimensions no confinement, but you have some tight harmonic confinement in one direction. Right. So while the atoms are at distances smaller than that confinement, it's a 3D problem. As soon as the 3 atoms start getting large from each other, distant from each other, at distance larger than the transversal confinement, then start behaving more like a 2D problem. Right. But in reality, the number of degrees of freedom is still 3 for each particle. All right. This D that you vary is just a simple, is a mathematical curiosity. So when you squeeze the gas,
your point.
or more, there's no effective dimension. I mean, maybe I think I remember hearing about fractional dimensions in chaos or. But
yes, but some topological problems. Yes, but it's not the case.
Yeah. You can see. Yeah, you can start squeezing your system and see FMOV states disappearing, okay? Because of this effect is depending on if the size of the FMOV state it's smaller than your tightest of the confinement, right? It's good. It's behaved just like a 3D FMOV state. But if your trimer start increasing, it becomes larger than your confinement, then you start feeling effects of a confinement. And if you start squeezing even more, that state might become unbound. Right. But still, I feel like the dimension is not really tunable. I think it's an interesting mathematical. Yeah. Hmm?
Exactly what Brandon said. This is the parameter that you tune, and then it is a question of how large is your trimer, whatever, is compared to this one dimension. And if you compare, that's what you were saying, you might cast that into a parameter that you call D, but for me it has, I would like to see then the spectrum or whatever dependent on that parameter, for example. Yeah. But as I said, it's not the only parameter that you have to worry about here in this problem.
Like, for instance, you're saying dimension 2.2, all right? It still has FMOV states, FMOV effect, which means you would have an infinity number of 3-body states with the sizes increasingly large. Yes. If you squeeze in an experiment, if you make one of the confinement tight, you always are going to have just a finite number of FMOV states.
No, okay, experimentally you're right, but these okay, you are measuring not infinite number of 3-body bound states. Okay, you have it's limited by the size
just
of your trap.
In your Hamiltonian, right? You don't need to do experimentally, but in your Hamiltonian, you put a confinement in one of the directions. That's going to limit the number of states you can ever have.
Yeah, I guess I'd like to see this related to things like the Olshani mapping. You know, if you really squeeze one dimension, or say 2 dimensions into a cigar-shaped geometry, right? You know, you can map that onto an effective one-dimensional coupling constant or scattering length, and then in that limit where you're maybe in the lowest oscillator mode in whatever the small dimensions, then you can presumably write it as an effective 1D or an effective 2D Schrodinger equation with effective 1D or 2D scattering lengths. But again, that's how I would like to think about this, and I think it's more experimentally relevant than trying to map it onto a fractional D.
Yes, for me, it all is not clear what's the interpretation of some fractional dimension. But I got your point. I didn't think in that direction. Okay.
Okay, I don't see any further questions. So let's thank all the speakers again.